Good morning, everyone. Let's continue talking about applications of vectors. Today we'll continue our conversation about the dot product, but this time of algebraic vectors. Please notice the key words, algebraic vectors. Now, yesterday we talked about the dot product, but we only looked at geometric vectors. Today we'll bring in the power of algebra. So let's get started. I have here two vectors. Let's consider the coordinates of point A as A1, A1, A2, A3, and point B of coordinates B1, B2, B3. Please notice that I am talking about vectors in 3D in R cubed. Good. So I have here my two vectors OA and OB. By definition from yesterday, I know that the dot product of, how about I call the blue vector A, I'm going to call it A, and the green vector, I am going to call it B. Good. So what I know from yesterday, I know that by definition the dot product of A and B is nothing else but magnitude of vector A times magnitude of vector B times cos of angle alpha, where angle alpha is nothing else but the angle in between these two vectors. The red angle is alpha. Good. So that was my definition from yesterday. Now, this time my vectors are in a coordinate system. So I threw the vectors in a coordinate system, and I want to see if that helps me to get a new definition for the dot product. Okay, so let's see. Let's take a look a little bit at the definition of the dot product. What do I know about? What do I see? Have I ever seen in my life this part over here? Nothing else but magnitude of A times magnitude of B times cos alpha. Have I seen that before? Of course I did, and the answer is when I used the cosine law, in what triangle? In triangle OAB. Of course, when we apply the cosine law in that triangle, that part, this part over here, will be part of it. How about we try to do that, applying cosine law in triangle OAB. First of all, how about I do triangle OAB? I'm going to do it as a vector. I am going to do it as a vector. There you go. This is my vector. Vector AB. We'll see if that's what we need. Doesn't really matter because I'm going to use magnitude. So I can write easily that magnitude of, applying cosine, magnitude of AB squared, which is nothing else but length of segment AB, is nothing else but magnitude of OA squared plus magnitude of OB squared minus 2 times magnitude of OA magnitude of OB cos of angle in between, cos alpha. Okay, so let's move on. Magnitude of AB, nothing I can do about it. OA, my short name for OA is vector A squared plus vector B squared minus 2 times magnitude of A, magnitude of B, cos alpha. So basically, what I am trying to get here I am trying to get to this part over here, magnitude of A times magnitude of B times cos alpha, which is nothing else but the dot product of A and B. We all agree. Nothing else but this part over here is nothing else but the dot product of A and B. So basically, I need to express this, this, and this. And if I have those three parts, I will automatically get the magnitude of, if I have all those three magnitudes, I will be able to come up with another expression for the dot product A and B. Good. So how about we start with an easy one? Let's start with the magnitude of A squared. Well, if I go to my diagram, vector A is a position vector. So if I apply the Pythagorean theorem, I'm going to get square root, but no square root because I am interested in magnitude squared. So I'm going to get A1 squared plus A2 squared plus A3 squared. Absolutely identical. I can get that magnitude of B squared will be, again, go to the diagram. OB is a position vector, apply Pythagorean, and the magnitude of that vector will be B1 squared plus B2 squared plus B3 squared. Good. So life is good. Now, I have a little bit of problem with vector AB. How about I try to write in triangle OAB, let's try together to write vector AB. You know, I'm not good with addition of, with subtraction of vectors. However, I know I can write something like that. OA plus AB equals OB. Let me double check to make sure this is right. OA is OB. Yeah, that's fine. Or, in other words, let's group these and let's take them with us down. Okay, so let's move on. Okay, so in other words, I can write that vector AB is nothing else but vector OB minus vector OA. Well, you knew that. It's not a surprise for you. As a result, AB can be written as OB was vector B, short for B minus A, or using the two components, vector B is B1, B2, B3 minus vector A using components A1, A2, A3. As a result, vector AB will be nothing else but B1 minus A1, B2 minus A2, B3 minus A3. Good. So that is my vector AB. One more step I need to calculate the magnitude of AB. What is the magnitude of AB? Well, actually, I'm going to need it squared, and that makes my life easier. Well, exactly like I did before, is B1 minus A1 squared plus B2 minus A2 squared plus B3 minus A3 squared. Good. So life is good. Let's see the important relationships that we're gonna use from this point on. What do I need? I need number 1, I need number 2, and I need number 3. These are the 3 expressions that I need. Whatever is in between right now, I don't need. So how about we move it out of the way? We don't really need it now. Let's move it. Let's make it smaller, and let's move it out. Good. So the 3 expressions that I need, And this one, again, I don't really need it. I got the idea. These are the three expressions I need right now. Good. Okay, I'm gonna move this up here. Good. So now I have the three expressions that I need to apply in the cosine law. Do not forget, one more time, my objective is to isolate the dot product. Okay, so let's happily start substituting all the values there. Make this smaller, put it here, so I have it under this one, make it smaller, and let's put it right here. So this expression, the green expression, becomes b1 minus a1 squared plus b2 minus a2 squared plus b3 minus a3 squared equals a magnitude of a squared. That's given by expression number 1, so it's a1 squared plus a2 squared plus a3 squared plus magnitude of b squared is from expression number 2, b1 squared plus b2 squared plus b3 squared minus 2 times the dot product of a and b, exactly what I'm looking for. Okay, so let's expand here. Let's see what happens. b1 squared minus 2a1 b1 plus a1 squared, let's not mess up the algebra, plus b2 squared minus 2 a2 b2 plus a2 squared. So I am done with this, I am done with this, this one I have left, plus b3 squared minus 2 b3 a3 plus a3 squared equals, the other side I will just copy for now. It's a1 squared plus a2 squared plus a3 squared plus b1 squared plus b2 squared plus b3 squared minus 2, the dot product of a and b. Okay, look how lucky we are. What happens with b1 squared, b1 squared, a1 squared, a1 squared, b2 squared, b2 squared, a2 squared, a2 squared, we are very lucky, b3 squared, b3 squared, a3 squared, a3 squared. From this ugly expression, the only things left are minus 2 common factor, and in a bracket I have a1 b1 plus a2 b2 plus a3 b3 equals negative 2, the dot product of a and b. As a result, we can say that whenever two algebraic vectors are given, the dot product is a1 b1 plus a2 b2 plus a3 b3. Please pay attention that everything we have done here represents nothing else but the proof of the dot product, which is mandatory for us. It's a nice and beautiful proof. It's mandatory for us. Now, what I wanted, let's see how we are doing. Oh, okay. So we'll stop here and we'll continue the discussion in class.